Hey everybody. So I made a video here, making the video of what lesson that we were going to do in class on Wednesday when I had, some issues with Google Meet. All right. So we are starting brand new chapter. All right. As you can see, chapter 2, derivatives. There's basically two huge topics that you talk about in calculus this year. And the first one is derivatives. Okay. Derivatives is something we're going to use the entire year. If you were to keep taking more calculuses in college, derivatives are something we come up with all the time. So today is just going to be a basic introduction, all right, to derivatives, and then go through a little bit of notes here. Obviously, I'll go over this in class next time we meet again, but just want to give you a little bit of sense so we don't fall too far behind of what we were going to do on Wednesday. All right. Now, first thing you see here is tangent lines. If you remember from geometry, like we talked about a tangent of a circle, a tangent line to a circle, and it was a line that only hits the curve once. Remember, it was like here, and it goes something like this. And you draw a tangent line, it only intersects the circle in one spot, right? So the problem with that is, all right, so that only hits in one spot, that only hits in one spot, no big deal. Problem is, what if you have a curve like this second one? Well, I can draw it so it only hits that in one spot, but if I continue, well, that wasn't the best drawing in the world, Mr. Goer. Could draw it a little bit better so that it can intersect more than one spot, all right? Hits there, so that's not good, all right? So the new definition, all right, is the limiting line on the set of secants PQ as Q approaches P. Like, what does that mean? All right. Well, I'll explain that in a second. All right. So basically what it means is this. As Q gets closer and closer to P, the secant line PQ gets closer to the tangent line. Okay. So if I were to look at this example here, okay, point P, it says draw the line tangent to point P. All right. So if I were to take a point that's here and connect it, all right, it's just that line. And even if I moved it closer, it's this line, right? If I move it there, it's that line, right? The tangent to a tangent to a straight line is the line itself. Well, not a straight line, every line's straight. A tangent to a line is the line, all right? So when it says the limiting line, what we are actually doing is looking at, just we do with limits, looking from the left and to the right. If it's the same line, that's going to be our tangent, okay? So on the left side, the tangent to the point P is just this line itself. On the right side, if I took a point here, as I get closer, they're all going to be, it's a straight line. It's just this. So from the right side, it's this purple line. From the left side, it's this, it's that red line. All right. Well, are they the same line? No. So there is no tangent. All right. Now, every time you have a situation like this is a special. What's going to happen here is a lot of special circumstances. All right. If I were to just erase these, we call this a corner. All right. Because the point is like at a corner, right? You have a straight line coming up, goes right to another straight line. All right. So we call this a corner. There will never, ever, ever be a tangent line at a point that's on a corner. All right. It won't happen. All right. Now, you're probably right now like, what are you talking about? The more we do these, you eventually will get it. All right. This first lesson is a lot of like, it's almost like in geometry, a lot of technical stuff goes on, but eventually we'll get the hang of it. All right. So for B, if I took this point here, remember, this is a straight line. So a tangent to a line is that line. So the tangent to a straight line is just that line. But if I go from this side, it's also this line. So the tangent is just that line itself. All right. So anytime a tangent to a line is the line. Tangent to a line is the line. So if I ever say draw a tangent to a point, to the point, and it's on a straight line, the answer is the straight line. All right. So C. All right. Now, I have point P. Let's say I took a point here and I drew a line, a secant line connecting. Secant line, remember, secant line is just a line that goes through like this of a circle, right? So if I have that and I connect these 2 points, I know it's not a perfectly straight line, but all right. Then if I move closer, it looks like this. Looks like that. As I get closer and closer, what is happening to my secant line? Because remember, the definition says, well, here it says, as the secant line, PQ, gets closer and closer to the tangent line. So it was this line, then this line, and that line. Doesn't it look like more and more that it's becoming a horizontal line almost, right? That pink line right there. See, it was here, it was there. So as that point moves closer and closer and closer, it's getting more and more on the left side like a horizontal line. Now, what happens on the right side? So if I start here and connect the points, it looks like that. If I get closer, it looks like this. Now, what kind of line is it looking more and more like? Well, not a horizontal line, but a vertical line. So from the right side, it's a vertical line, the tangent. From the left side, it's horizontal. So are they the same? No. So there is no tangent. All right, there is no tangent. All right, now let me erase this for a second. So this special case is what we call a sharp turn. All right, this is a sharp turn. There will never be a tangent at a sharp turn. All right, we were going up, and then it's like, whoop, skirt, go down this way. All right, never will be a tangent at a sharp turn. All right, so for D, if we take a point on the left side and draw a line here, but then if I get closer, I draw a line there, get closer and closer, line there, line there. What's it looking more like? A vertical line. From the right side, what's happening? Well, let me do a different color here. If I took a point here and connected it with P, looks like this, looks like this, looks like getting close. They both are vertical lines. So the tangent to this little thing right here, we'll call this like a cusp, is a vertical line. All right. So anytime a situation like that, that is a vertical line. All right. E. Well, if I go from the left side, it's that straight line. From the right side, it's that line. Is it the same? Nope. So there is no tangent. All right. Basically, what's going on there? It's a jump. All right. It's a discontinuity there. So we have no tangent line. All right. Scroll down. All right. So the slope of the tangent line, well, meaning you can't have a slope if there is no tangent line. All right. So where does the slope of the tangent line fail to exist? Well, that means basically where is there no tangent line? Well, where there is no tangent line are any discontinuities. So anytime you have a hole, a jump, or an asymptote. Okay, so you will never have a tangent line in any of those situations. All right, you saw in example E here in that this was a jump and there was no tangent line. All right, also at any corner, like example A, or sharp turn like C. All right, also there will be no slope of a tangent line when there is a vertical tangent like D, because the slope of a vertical line is undefined. All right, so the slope of the tangent line fails to exist either at a hole, jump, asymptote, a corner, a sharp turn, or a vertical tangent line. Now, why is that important? Well, the reason we care about that is because of differentiability. All right, differentiability. Sorry, it's a tough word. Are places where you can find the slope of the tangent line. All right, so the places where something will not be differentiable is any of these examples. Hole, jump, asymptote, corner, sharp turn, vertical tangent line. Besides that, you should be able to find the slope of the tangent line, and those places would be differentiable. All right, differentiability implies continuity. So meaning if a function is differentiable, then the function is continuous. This statement is not reversible though. It is not true that just because a function is continuous, then it has to be differentiable. All right, so for example, all right, this function here, this is a continuous function, right? There's no jumps, holes, asymptotes, whatever. This is continuous, all right? However, if I were to try, the tangent does not exist to this because it's a corner. All right. So this is continuous, but it's not differentiable. So just because something is continuous does not mean it's differentiable. All right. And the reason it's not differentiable is because there's no tangent line here. It's like example A. All right. We have a corner. All right. So wherever there's a corner, we have no tangent. All right. Wherever there's a corner, we have no tangent line. All right. All right. If we look at example B, all right, this is a continuous function. All right. Right. But let's look at the tangent. So like as I get closer to this like little like S curve thingy here, right? Here, be a line here. This point be a line there. There. You see how it's becoming a vertical line? And the same thing's happening on the right side. So the tangent of this is a vertical line. However, vertical line has no slope, right? It doesn't have a slope. So this is, once again, this is continuous, but not differentiable. So these are both examples where something is continuous, but not differentiable. And that's because it has a vertical tangent line. So where it's not differentiable is where there is no tangent line or it has a vertical tangent line. All right, so we're going to practice a little bit more of this right here in this picture. All right, it says list the places where the function is not differentiable. So all the x values where it is not differentiable. Okay, now, all right, so what we are looking for where there's a hole, a jump, an asymptote, a corner, a sharp turn, or a vertical tangent line. If it happens at any one of those places, then it's not going to be differentiable. All right, it's not going to be differentiable there. All right, okay. First thing, -4. See, this is an endpoint. Guess what? It's not going to be differentiable at an endpoint. So x equals -4. So at an endpoint, it's not differentiable. All right, -3. What is happening at -3? Well, we have a corner. All right, this is a corner. All right, that's a corner. So it is not differentiable there. All right, what's happening at -2? We have a jump. All right, so we have a jump, which means it's not differentiable. What's happening at -1? We have a hole, which means it's not differentiable. What's happening at 0? We have an asymptote, which means it's not differentiable. All right, what's happening at 1? We have is that differentiable? No, it's a sharp turn. What about 2? Well, let's look at 2. All right. All right, 2, as I get closer and closer, what kind of line does it look like it's going to be? Well, it's going to be a horizontal tangent. It has a tangent. It's horizontal, which means it is differentiable, so we don't list it. Now, if we look at 3, 3 is going to be more of a vertical line. Vertical line is a tangent line, but it doesn't have a slope, so it can't be differentiable, so we have to list it there. And then 4, can't really see the point. 4 is not an endpoint because it has an arrow. All right, 4 would have a tangent line that looks something like that. So it is differentiable there, so we're good. So there are your answers. Now, a lot of people have a question of like the difference between an S curve that looks like this, where you got a point there, or one that looks like that when the point's there. Okay, so just imagine, remember, as you're trying to find what the tangent would be, if you took a point on the one side, drew a line there, here. As it get closer, do you see how that line is becoming more horizontal? Same thing if I did different color here. Let's do like yellow. It's going to show up well, but we have that line. Then I get closer. See how they're both becoming more horizontal since it's the same? That's why it's horizontal. We have one like this, point here, it's there. You could draw straight lines there. It's coming more vertical. All right, so vertical lines are no good. That's why it's part of the thing, because it's not differentiable there. Horizontal lines are fine. It is differentiable. That's why we don't list it. All right. All right, so last thing, and the most important thing of today is actually the definition of a derivative. All right, and I will ask you this probably a million times through the course of this year. What is the definition of the derivative? A derivative is the slope of the tangent line. All right, a derivative is the slope of the tangent line. Okay, now a lot of stuff going on here. But what you need to know for the slope, the definition of what we call the definition of the derivative is this right here. All right. M, member, stands for slope. Tan means of the tangent. It is the limit as delta x approaches 0 as f of x plus delta x minus f of x all over delta x. That's what it is. So it's the limit as delta x approaches 0 of this thing right here. You have to memorize this. You're like, I can't memorize that. Yes, you can. We'll use it enough, you'll memorize it. All right. So it's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay. Now, this explanation, where they get this from, what they're saying is, if you remember the slope formula, all right, and remember how the slope formula is like, what is it? y2 minus y1 over x2 minus x1, right? All right. Well, if you have point Q and point P, right? And if we call this point here x, and then instead of y, we're just going to call it f of x, which is the same thing, right? X and f of x. So then we go over a certain amount. We're going to call that delta x, which means the change in x. So if this x coordinate was x, then this new one, whatever it is going to be x plus whatever delta x is. That's where this comes from. Then to get the y, you would just plug this into the function. So that's where you get f of x plus delta x. All right, so if we're doing the slope, all right, y2, it's f of x plus delta x minus y1, which is f of x, all over the two x coordinates, which is x plus delta x minus x. Well, the x's cancel, leaving you with f of x plus delta x minus f of x all over delta x, right? So that's this right here, all right? That's just any secant line. So that's like the slope of that line. Well, as p gets closer and closer, right? As we get closer and closer, this distance here is getting as closer and closer, it gets smaller and smaller and smaller. So eventually it gets to 0. And that's where the limit as delta x approaches 0. And that's going to tell us what the slope of our tangent line is, because the tangent is the line that's created as we get closer and closer with our secants. All right, so that's where it comes from. Do you really need to know that? No, but just thought I'd give you a little background. What you need to memorize is the definition of a derivative. The definition of a derivative is the slope of the tangent line, which is the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. All right, so what we're going to do is we're going to use the definition of the derivative to find the slope of the tangent line of f of x equals 3x plus x squared. All right, so we are going to use our thing. I'll write out the definition, all right? So it's the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay. All right. So what we're going to do is like 3 parts. The first part is this one right here. All right. Where we are going to plug in x plus delta x into our function right here. All right. This is our f of x. So I need to take x plus delta x, and wherever I see an x, I have to replace it. So it's going to be 3. Oh, instead of x, I have to put x plus delta x minus, instead of x, I got to go x plus delta x squared. All right. So all I did was, remember, when you have a number, whatever you have in parentheses, you replace that in your function, whatever you replace x with whatever that is. So I replaced x with x plus delta x there, and replace this x with x plus delta x. All right. So now the second part is minus f of x. Well, it just means minus the original. Minus, put in parentheses, 3x minus x squared. All of that over delta x. All right, so that's just me substituting it. Now I just do algebra. Now what will happen, this is very important, You will always have things canceled up top. Anything that does not have a delta x in it, any term should cancel. If it doesn't, you did something wrong. Okay, we'll do a lot of these examples, so you'll get that through. You'll start to understand it. But if a term doesn't have a delta x in it, that means that it should cancel up top. All right. So, because right now I can't just do this limit because I can't just plug in 0 for delta x because it's got 0 in the bottom. All right, so let's multiply this out. I get 3x plus 3 delta x minus, x plus delta x squared. So x times x is x squared. X times delta x is x delta x. Then there's going to be 2 of those. So it's going to be 2x delta x. Delta x squared is delta x squared. Delta x times delta x is delta x squared. Minus 3x plus x squared, because I needed to distribute the negative. All right, so just so I have to write all this out again, if I would distribute this, I would get a negative x squared, a negative 2x delta x, and a negative delta x squared. All right, so this is now gone, and I have that. Okay, now what I said is everything that does not have a delta x should cancel out. So this 3x doesn't have a delta x in it. There better be a negative 3x. There is. It's right over here. We have 3 delta x. That's fine. Oh, negative x squared should cancel out something. It does. The positive x squared. They get a negative 2x delta x and a negative delta x squared. Fine. All 3 terms have a delta x in them. So what's going to happen every single time? I don't know why I have x squared. Should be delta x on the bottom here. What you're going to do is once you cancel everything on top, your next step is to take out a delta x, because since all of them have a delta x in it, you can pull one delta x out. So it leaves me with 3. Negative 2x delta x leaves me with a negative 2x. If I had a delta x squared and I take one out, I'm left with negative delta x. And the reason I'm always going to take out a delta x is because I need to cancel that with the bottom. And that will happen every single time. So you're going to cancel up top anything that doesn't have a delta x in it. All right. Then you're going to pull out a delta x, and you're going to then cancel out. And as soon as you cancel, just like we did with our limits, we then substitute in 0. And when I substitute in 0, that's gone. And I'm left with 3 minus 2x. And that is the derivative. That is the slope of the tangent line. All right. That is the slope of the tangent line. All right. Now we're done. That's your answer, 3 minus 2x. Right. Now, for this one, use the definition of the derivative, find the slope of the tangent line for this function, add x equals 4. All right, well, let's not worry about add x equals 4. Let's just do the same thing we did above for this. All right, so let's see if we can find the derivative for 2x squared minus 3. All right, so we're going to use the definition of the derivative. All right, so the first thing I need to do is plug in x plus delta x for that x. So 2, instead of x, I put x plus delta x minus 3. All right, so that's the first part. That's this part right here, right? That's the f of x plus delta x. Now I got to do minus f of x, which is that. Put in parentheses 2x squared minus 3, all over delta x. And remember, this is the limit as delta x approaches 0. All right, so this was my f of x plus delta x. This is my f of x, right? This is me just plugging in x plus delta x in for that x. And I forgot something here. It should be squared. Okay, now I do my algebra. Now we already know what x plus delta x squared is. This thing right here. It's x squared, right? So it's x squared plus 2x delta x plus delta x squared minus 3, distribute the negative, negative 2x squared plus 3 all over delta x. Okay. Then I multiply all those by 2, so it's 2x squared plus 4x delta x plus 2 delta x squared minus 3 minus 2x squared plus 3 all over delta x. All right. So now remember, anything that does not have a delta x should cancel. 2x squared, negative 2x squared, negative 3, positive 3. The only two terms I have left, 4x delta x and 2 delta x squared, are both have a delta x in them. And so our thing to do is then take out a delta x. Yes, do they have a 2 in common? Don't worry about it. Just take out the delta x. I am left with a 4x, and I am left with a 2 delta x. And I take all over delta x. So as I take out the delta x, I am going to then cancel. So I'm left with 4x plus 2 delta x. I then plug in 0. 2 times 0 is 0. So the derivative is 4x. That's the slope of the tangent line. Okay. Now, let's go back and look at what this means at x equals 4. So this 4x will tell you what the slope of the tangent line is at any point x. Well, all you have to do to figure out the specific one is plug in 4. So 4 times 4 is 16. And there's your answer, 16. If it had said, what is it at x equals 6? You do 4 times 6 would be 24. Same thing for this one. This is just telling us at any point x. If we could have done the same thing, I could have said, well, what is it at x equals 3? You plug in 3 and it'll give you the exact answer. All right. So the derivative gives us the slope of the tangent line. If I want a specific x value, you just plug it in. That's it. All right. All right. So we are going to stop there. All right. As you can see from this note sheet, there is, a lot of different questions, but they all come back to, the definition of the derivative and the slope of the tangent line. All right. I expect there to be questions after this, which is fine. All right. But at least now you have this video, they can always go back and reference to go back over some things. I'll go over a lot of this again in the next class, but please make sure you check out this video before, hopefully you've watched this video before we meet again. All right. Enjoy the rest of your weekend or day, when you watch this. All right. Bye.